Assalamualaikum and good afternoon to all. I am Nur Habzan binti Bariman from Polytechnic Muazzam Shah Pahang. Today I want to present about optimization of laser melting parameter to enhance surface properties in hot press forming dies. Before start, let me brief about presentation outline. First, introduction. Second, laser melting process. Then DOE optimization, metallographic. Then surface morphology, hardness properties, boron steel properties, and last conclusion. Laser is a device that generates light by a process called stimulated emission. The acronym laser stands for light amplification by stimulated emission of radiation. The laser system applied in medical, military, and manufacturing sector. Laser in manufacturing divided for three classes. First, laser surface with melting. Second, laser surface without melting. And the last, laser surface melting with addition material. Laser surface with melting produce very rapid heating and cooling on melt surface, that is melting and glazing. While laser surface without melting is a surface of material not melt, where the material surface in solid state transformation. Laser surface melting with addition is surface of material melt with added same or different material. Laser melting produce homogeneous and ultra-fine structure of surface with rapid solidification. The laser melting improve properties of wear resistance, toughness, and hardness. Usually, hardness of melt surface increase up to more than 600 hardness Vickers. Figure show laser melting process with conduct using Nd:YAG laser with 1064 mm wavelength with pulse mode. In this study, argon gas used to prevent sample from oxidation during laser melting process. The experimental data were analyzed using response surface method RSM with Box-Behnken technique to analyze surface response on melt surface. DOE analysis showed the effect of peak power, pulse repetition frequency, PRF, and overlapping percentage on hardness properties, surface roughness, and melt depth of the sample. The goal, limit, and important level for setting an outcome parameter from DOE are shown in this table. The goal of peak power, PRF, and overlapping rate were set within the appropriate range of is in range. The hardness properties goal were set to maximize, while melt depth was set to minimize, and surface roughness set is in range. The important level for factor parameter were set at level 3 for all parameters. The important level of hardness was set at level 5, while the roughness was set at level 3 and melt depth was set at level 2. The change on the important level will affect the desirable solution. This figure shows the summary of DOE optimization of quadratic model of surface hardness, roughness, and melt depth. DOE optimization conduct to get optimum laser melting parameter and finding, and validation process conduct to prove that parameter used is valid. From the quadratic model, the optimized parameter are listed. Parameter number 1 has a highest desirability. This DOE suggests the best parameter was at peak power 2500 watt with PRF 58.27 Hz and overlapping rate at 30% with 0.847 desirability to get optimum hardness, melt depth, and roughness. While from experimental, the optimum result produced at peak power 2500 watt with PRF at 60 Hz and overlapping rate at 30% with 793.7 hardness Vickers with melt depth of 0.21 mm and roughness at 3.89 micron meter. Result from relative error for surface hardness shown 0% relative error for parameter number 1, while 1.1% relative error for parameter number 9 and 1.5% for parameter number 11 from DOE Optimisation analysis. These parameters are within a defined confidence interval which verify the model. Figure show formation of three layers after laser melting process, namely melt zone, heat affected zone, and substrate. Melt zone produce refined grain structure of 1.02 micrometer average grain due to localized rapid heating and cooling, while heat affected zone produce coarse grain structure due to delayed solidification, where the temperature between liquidus and solidus cause partially melting. And last is a as-received H13 steel or substrate with distribution of carbide with 3.12 micrometer average grain size. The grain structure at melt zone refined due to rapid heating and cooling during melting process and contribute to increased hardness in melt layer. Highest melt depth of 0.33 mm due to higher energy penetration in melt depth shown at 70% overlapping rate in that figure. Longer interaction time and slow solidification in melt pool produce deeper molten pool at 70% overlapping rate, and lowest melt depth produced at 30% overlapping due to laser penetrant reduce laser energy absorption into sample surface at 30% overlapping, where the melt depth is 0.24 mm. The surface hardness in melt layer increase regardless of overlapping percentage, where the higher hardness at melt layer shown at 30% overlapping rate due to rapid heating and cooling produced from high processing speed. And lower surface hardness produced at 70% overlapping rate with 672.1 hardness weakness due higher overlapping rate pattern cause lower cooling rate at melt pool. Hardness at heat affected zone area decreased due to shorter interaction time and delayed solidification. This region called as partially melt zone. Hardness at melt zone increased due to grain refined after laser melting process. This result show microstructure and hardness properties of boron steel responding to die insert. Figure A show microstructure of as-received boron steel before HPF process with 202.5 hardness weakness. Next, shown microstructure B with 85.7% martensite after HPF process using as-received H13 die insert produced 386.6 hardness weakness. While when the boron steel pressed using melt die insert, the boron steel hardness increased up to 508.1 hardness weakness. At this hardness, the martensite percentage is higher at 76.3 to 80.6%. Effect of surface morphology reduce effect of metal to metal contact and increase surface hardness of boron steel after HPF process. In conclusion, this research is significant to hot press forming using laser melting die insert can improve the die performance where optimum processing parameter increase die hardness 3 times up to 793.7 hardness weakness due to grain structure refined up to 1.0 micrometer and roughness or texture of melt surface improve with low processing speed. While hardness of boron steel increased 2.5 times up to 508.1 weakness produce high strength component and improve strength of boron steel. Thank you.